Hi, I'm Ollie, and this presentation is a complete walkthrough of our fixed-wing aircraft design project of excellence. I'll be covering a full engineering process, from defining the problem to design and modeling, construction, electronics integration, testing, and finally, our flight day performance. The design challenge was to design and build a remotely controlled fixed-wing aircraft capable of flying a figure-8 course around the football field in the shortest time possible. The key is that speed only matters if the aircraft is stable, controllable, and reliable. Because if the plane stalls, drifts off course, or becomes unpredictable, the run ends immediately. From the start, our strategy was to treat this like a real engineering project. Start early, build early, and test early, so we could spend the most time where it actually matters, learning flight behavior, diagnosing issues, and improving performance through iteration. During our research phase, we focused on understanding what design features are commonly used in stable fixed-wing RC aircraft. Since this was our first RC plane build, we didn't want to invent an entirely new configuration with no reference point. Instead, we took inspiration from designs that are already known to fly reliably and consistently. A major source of inspiration was flight test. Their aircraft gallery and flight videos allowed us to compare different trainer designs and see how individual features affect real flight behavior. We referenced planes like the Old Fogey, Bushwhacker, and Tudor, paying attention to things like stability, turning behavior, and how forgiving the aircraft looked during minor mistakes. Another major influence came from a field trip to the airshow, where we spoke with an experienced RC aircraft builder. That conversation didn't just answer questions in the moment, it turned into an ongoing resource for us. That guidance helped us avoid a lot of dead ends, stopped us from overcomplicating the project, and played a big role in how early we were able to get a working aircraft in the air. More than anything, that experience showed us the value of making connections in engineering. Overall, our research phase was about identifying proven design elements and understanding why they work, so we could apply those principles to our own aircraft. We began the design process with hand sketches. Sketching was how we turned general ideas like wanting stability or slow flight into actual geometry. The sketches allowed us to decide exact dimensions, wing layout, and tail configurations before anything was actually built. At this stage, we locked in several major design choices. We committed to a high wing configuration, tip dihedral, and an undercambered wing, all based on our goal of building slow, stable aircraft that would be easier to control during the course. Once the concept was established on paper, we transitioned into Autodesk Inventor, which became one of the most important tools of the project. We started by building a full 3D model of the aircraft. The 3D model allowed us to visualize how all major components interacted as a system, including the wings, fuselage, empennage, and power pod. It helped us refine proportions and confirm that everything fit together logically before construction. After the 3D model was finalized, we generated 2D drawing sheets from the model. These acted like construction plans, clean views with accurate dimensions that we could reference while transferring measurements onto foam board. In other words, the 3D model helped us design it, and the 2D drawings helped us build it accurately and consistently. For reference, the final aircraft was designed around a 37-inch wingspan, a 10-inch wing chord, and an overall fuselage length of about 31 inches. Overall, this CAD workflow wasn't just for visualization. It directly guided construction and improved accuracy throughout the build. For control, we kept it simple with just an elevator and rudder. The elevator controls pitch, so it sets the climb angle, helps maintain altitude, and also lets you recover smoothly if the nose starts dropping. The rudder controls yaw, which we use to start turns and correct heading. On our aircraft, rudder inputs also help the plane bank into turns because the dihedral naturally converts some of the yaw into roll, so turns felt smoother and more predictable. We originally considered ailerons, but we removed them to reduce complexity in both electronics and piloting. With dihedral and rudder-based turning, we could still turn effectively while keeping the control system more reliable for a first-time build. We constructed the aircraft primarily from foam board because it's lightweight, easy to work with, and quick to repair. Since crashes are inevitable during flight testing, foam board allowed us to iterate without losing significant time. Structurally, the most critical areas were the wings, which define aerodynamic behavior, and the nose and power pod, which experience impacts and vibration. These areas were reinforced as needed while keeping the overall weight low. The completed aircraft had a mass of 575 grams, which served as the payload mass on race day. Our propulsion system used a 1000 kV brushless motor paired with a 9x4.5 propeller, controlled by a standard electronic speed converter, or ESC. This setup provides steady thrust without forcing excessive speed, which matched our slow fly trainer style design approach. One major lesson we learned is that propulsion systems are especially vulnerable to damage. Even small impacts can bend a motor shaft, and once that happens, thrust drops significantly, even if the motor still runs. For our electronics and RC control system, we kept the setup simple and reliable. We used a FlySky transmitter and receiver, an 11.1 volt LiPo battery, an ESC, a brushless motor, and 2 servos, one for the elevator and one for the rudder, connected through the receiver with push rods and control horns. Our electronic total cost was around $120. Functionally, the battery powers the ESC and motor for thrust, while the receiver takes the radio signal and commands the servo for pitch and yaw control, with the ESC also providing regulated power to the receiver and servos. We mounted everything using a swappable power pod so it was easy to access for repairs and stayed secure to keep balance consistent between flights. Testing was the most important part of this project, and it's where we learned the most. We began flight testing much earlier than most groups, and those first flights were a huge confidence boost. The aircraft took off cleanly, maintained altitude, and responded well to control inputs. While many teams were still working to get a plane built, ours was already flying. That early start shifted our focus away from the basic functionality and toward refinement. Instead of asking if the plane could fly, we were working on how well it flew, practicing piloting, improving throttle control, and dialing in smoother turns and landings. Those early flights proved the design worked, and from that point on, testing became about consistency, control, and preparing the aircraft to perform when it mattered most. On time trials day, things didn't go well for us. We had built our first set of wings out of cheaper foam board, and under flight loads, they snapped down the middle. The wings essentially folded in on themselves. Once that happened, flight performance dropped immediately. We couldn't get a clean run, and most attempts turned to quick crashes because the aircraft just wasn't structurally sound enough to fly the way it had during testing. Instead of just guessing what went wrong, we treated it like a diagnosis problem. We went back and compared time trials footage to our earlier successful flights, and one detail stood out. The propulsion system wasn't producing the same thrust. The propeller was visibly spinning slower than before, which pointed to accumulated motor shaft damage over time. That combination, structural failure from weak wings and reduced thrust from a damaged motor shaft, explained why time trials looked so different from our early flights. After identifying the root causes, we made targeted fixes. The motor and shaft were replaced, the wings were rebuilt, and the key structural weak points were reinforced. Even with those repairs, it didn't instantly go back to perfect. Our first few flights afterward were still inconsistent as we worked out small issues, rechecked alignment, and dialed in throttle control. But once everything was finally tuned in, we had one of the best flights of the entire project. Over 40 seconds of smooth, controlled flight in a path similar to the course, followed by a proper landing. That moment was huge. It showed that the design worked when the aircraft was in proper condition, and that flight restored our confidence going into flight day. And honestly, that flight mattered because it wasn't just airborne, it was controlled. The climb was stable, the turns were manageable, and the landing was intentional instead of a crash recovery. It felt like the aircraft was finally doing what we designed it to do, which made flight day feel realistic instead of just hopeful. With that as our last major data point going into the event, we locked everything in, made sure the aircraft was ready, and went into flight day focused on executing. We had 2 official flight days. On the first flight day, conditions were extremely windy. Our aircraft was designed as a slow-flying, high-lift platform, and those conditions worked against us. Gusts caused the plane to pitch up repeatedly, and forward progress was difficult because the wind speed was close to the aircraft's airspeed. Even when the aircraft did get airborne, maintaining controlled flight wasn't realistic, so meaningful attempts weren't possible that day. The second flight day had much calmer conditions, and we had 4 official attempts. On the first attempt, the aircraft took off cleanly and immediately demonstrated strong lift. It climbed aggressively and pitched up more than expected. While correcting, the aircraft briefly lost orientation and recovered, but by that point it had drifted well off course. Rather than risk a crash, we cut the power and let it glide down for a controlled landing after about 14 seconds. The second attempt showed improvement. Takeoff and forward motion were more controlled and the aircraft stayed airborne longer, around 18 seconds. However, as we tried to correct heading, the plane began climbing again and eventually turned around, flying in the opposite direction of the course. Although the aircraft was still controllable, it was far enough off course that we again chose a controlled landing instead of forcing the run. The third attempt was the most promising at launch. The aircraft climbed strongly and looked stable, but shortly after takeoff, we experienced a sudden loss of power. The motor shut off unexpectedly and the aircraft nosedived into the ground. Possible causes include cold battery conditions, a loose electrical connection, or signal interference. That flight lasted only about 5 to 6 seconds. The final attempt was our longest flight of the day, lasting about 24 seconds. The aircraft took off well and initially flew smoothly, but struggled to build forward speed and experienced pitch-up stalls during turns. After recovering control, the aircraft crossed directly in front of the sun and the pilot lost visual contact. With limited visibility and decreasing control margin, the aircraft ultimately crashed into the bleachers, ending our final run. Even though we didn't complete the full course, our earlier testing proved the aircraft design was capable of doing so. Race day didn't reflect our best performance, but we were still the only group to achieve sustained flight, confirming the design worked and that the remaining challenge was consistency when it counted. Looking back, this project was defined by iteration, not just successful flights, but rebuilding and pushing through failure. Well, a few failures. Okay, a lot of failures. But that's aerospace. Every crash gave us feedback, and each fix made the next attempt better. It also reinforced the value of preparing early and making connections. Starting ahead and getting guidance early gave us time and direction to test, improve, and actually get a plane flying. In the end, we didn't get the perfect race day run, but we built a working aircraft, improved the design could fly, and we're leaving with real lessons we can apply to every project after this.